Hello and welcome back to yet another session on prescriptive analytics. In this lecture, in this video, we are going to talk about blending problems and how appropriate it is when we are looking at linear programming and how we're going to optimize for blending problems. So my name is Hari Rajagopalan and I will be conducting this lecture for this session. So let's take an example of a company, and the company's name is Agri Pro. They sell agricultural products to farmers. And one of the service it provides is custom feed mixing. So here a farmer can order specific amount of livestock feed and specify how much corn, grain, and minerals the feed could contain. And though this becomes very important from an agricultural perspective because various farm animals, the feed changes depending on weather, pasture conditions, and so on. So now Agri Pro stocks 4 types of feed that it can mix to meet a given specific customer's demand. And they received an order from a local chicken farmer for 8,000 pounds of feed. And the farmer wants the feed to contain at least 20% corn, 15% grain, and 15% minerals. Now remember, this is the minimum requirement. So we have 4 feeds that Agri Pro stocks, and they want to then now blend it together to provide this farmer this feed, right? And then there's the cost of these 4 feeds. So let's look at this table. So feed 1, feed 2, feed 3, feed 4. Here's how much percentage of corn is there. Here's how much percentage of grain is there. How much percentage of minerals, the cost per pound. And we've got to build a math model and solve it using linear programming. So remember, here's when take all this verbiage and filter out what is not needed and focus on what you need. So you received an 8,000 pounds. The table gives you cost per pound and percentage of ingredients in each feed, and the mix requirements. The 3 constraints for corn, grain, and minerals are given to you. So let's think through this problem, all right? So what is your objective? Remember, objective here, cost is given and you have to minimize the cost. You got to provide 8,000 pounds and you want to minimize your cost. The second part which you want to think about is what your decision variables are. And in this particular case, your decision variables, and let me get a pen here. So your decision variables, and a lot of times students go, well, we have to decide how much of corn, minerals, and grain we got to use. Well, remember, that's not in your decision mix. All you can decide is how many pounds of feed 1, feed 2, feed 3, feed 4, right? This is what you can decide, feed 1, feed 2. And so this is your decision variable. And when you mix these, you will immediately get your corn, grain, and minerals because this contains a mixture anyway. All right. So we are going to try and minimize the cost, right? So let x1 be pounds of feed 1, x2 feed 2, x3 feed 3, and x4 feed 4. And based on this mixture, we're going to minimize our cost. So objective is to minimize the total cost of filling the order. And of course, here we have 0.25x1, which is your 25 cents per pound, 30 cents per pound, and this is the cost, right? Subject to, you have to produce 8,000 pounds of feed. So x1 plus x2 plus x3 plus x4 is 8,000. In some ways, this is like your investments. Remember, when you had your investments problem, you had so much money, and you added up all the x's, and you got, this is the amount of money you have. Now, you also know that corn has to have at least 20% corn. So remember that each one of these mixes have some corn. So let's take example, right? 20% of 8,000 is 1,600. So x1, so if you take feed 1 and you take 100 pounds, 30% of it is corn, so 30 pounds will be corn. So it's 0.3 multiplied by x1. Similarly, if you take 100 pounds of feed 2, only 5% is corn, so 5 pounds will be corn. So it's 0.05 x2. Similarly, 0.2 x3 and 0.1 x4. All right. So now you can do this for grain, 15% grain. You got to look at how much percentage each feed has and multiply it times the percentage, right? Don't, on the right hand side, make sure that if this left hand side is in pounds, the right hand side is also should be in pounds. The most common mistakes I've seen students make is to say 20% here. This is left hand side is not 20%. This is number of pounds, and it has to be greater than certain amount of pounds, not percentage, right? Also, you can then put your minerals, 15% of minerals, and that should take care of your model, right? So now let's kind of go to Excel, and you'll see that Excel, as you see here, is the setup is very, very similar. You start with x1 to x4, you leave this cell blank, you put your objective coefficients, you put your constraint coefficients here, some products go down here, and then your right hand side values go here. Okay, so let's move on to Excel, and I will set this up. This will probably be the last problem I will set up for you, and then after that I'm not going to set up problems from scratch because I would expect all of you to be able to do this. So here's your Excel file, and I'm going to just go ahead and copy this and create a brand new worksheet, and we will start from scratch. And this is the last one I'm going to do from scratch. Okay, so once you've got your model, you start again, x1, x2, and then all the way up to x4, right? And I'm going to go ahead and let's get our, go center them because I like it centered. Now we're going to talk about the costs. Sorry, you leave the first row blank, right? This is your decision variable. Now you're going to look at your objective coefficients, and that's going to be 0.25, 0.3, 0.32, and 0.15. This is the cost per pound, and so this is in dollars. We will do the sum product a little bit later. So now order is for 8,000, right? Then we have corn is 0.3, 0.05, 0.2, and 0.1, and this should be greater than or equal to, and if I remember right, this came out to be 1,600, right? So we can actually just go ahead and copy this entire thing right here, right? And these are all greater than or equal to signs. So we have corn, grain, minerals, right? And so you could kind of go 0.1, 0.3, 0.15, 0.1 again. And for minerals, it's 0.2, 0.2, 0.2, and 0.3. And you got to use the sum product formula. So remember, it doesn't matter what model you are creating. You can just use the same structure. Don't forget to put the dollar, but you can create the same structure and use it every time. So you don't have to learn new formulas. You don't have to learn new setups. Now, some of the books have some really fancy methods. You are welcome to take a look at that. I will show you a different method for transportation problems, but here we'll just use the same thing again and again. All right. So again, go back to Analytics Solver and your optimization objective. You're trying to minimize this. Remember, the default comes out as maximum, so you want to change it to minimum. Your variables are right here. Your constraints, the first one is equal to 8,000, and then the other three are greater than and equal to their specific values. You're going to have to go to engine, assume non-negative is true, and then you click solve. That gives you your answer. It's asking you to use 4,500 feed 1, 2,000 of feed 2, 1,500 of feed T, and feed 3, and it's going to cost you 1,950, right? And that's exactly what we got here. All right, so we have finished with Excel. Now we're going to go back to PowerPoint, and we'll talk about something about the issues of scaling here and why that becomes important. Okay, so we got this answer, but I want to talk a little bit about models and their scaling. Take this constraint, mix at least 20% corn, right? So is written like this, it's 0.2 multiplied by 8,000. But it could also be rewritten like this. Take the 8,000 down here. You can say if we want the left-hand side to be a percentage value, we just would have to keep 0.2 here and divide this whole thing by 8,000. So 0.3 divided by 8,000 or 0.05 divided by 8,000 is a very, very small number, right? That's about, that comes to 0.0050625, right? So when solver is dealing with these very, very small numbers or large numbers, it's extremely inefficient for it. So storage problems may force the computer to actually use approximations, and such scaling problems sometimes prevent solver from being able to solve the problem accurately. So most problems can be reformulated or managed to minimize scaling effort. And the way we do it is to change the units. So instead of X1 saying pounds of feed to use, we use thousands of pounds. And when we start defining it this way, X1, X2 as thousands of pounds, the problem changes. So here we are minimizing the cost of filling the order. Now instead of 0.25, remember this is thousands of points, it's 0.25 per pound. So it's $250 for thousands of pounds. So these change. And the constraint now, X1 plus X2 plus X3, these are thousands of pounds. So that's equal to 8, not 8,000. 20% of corn. So now these are in thousands, right? The percentages remain the same. However, this will become 1.6, right? And again, 15% grain. So now suddenly, when these values are not divided by 8,000, it's divided by 8. Those are larger numbers. They're more reasonable numbers, and Excel works a lot better. So before scaling, the largest constraint coefficient was 8,000. The smallest one was, this very small number. Now we're kind of looking at between 0.00625 and 8. And so the problem is a lot more evenly scaled. So when you plug it into Excel and solve it, you'll get pretty much the same answer. It doesn't change, but you're resetting it, okay? So let me show it to you in Excel. I'm not going to walk through you step by step, but I'll just show you the answer in Excel. So here is the setup, the mathematical model, and you'll notice nothing much has changed. We continue to leave this blank. Let Excel put the values in. Here are the objective coefficients, which is exactly the same as this. Some product value, except here instead of 8,000 and 1,600, we're using 8, and nothing else changes. And when you solve it, you get the same answer. Okay, so this is an example of how we scale the problem. And from your perspective, you can either use this or you can use this model. Either way is fine. Just be consistent when you're using it. If you're going to do thousands of pounds, make sure that you are adjusting the models as it is done here.